Right, good morning. So, welcome to this presentation on understanding data inversion and inverse modeling. Michael, can you hear me okay? I can hear some typing. All right, where's the presentation? I can't see where it's here. Morning, Michael. We're just going to load the presentation. Morning, Maurizio, I can see you now. But I can't hear you. But do you want to put the presentation on? Sorry, some technical hold-ups here.
Yeah. Is mine now working?
Yeah.
Yeah, yours is working. Yeah.
Okay, sorry about the technical hold up there. Just getting the PowerPoint presentation up and running. Okay, well, welcome to this PoreXpert training session on understanding data inversion and inverse modeling. Let's have a look at the first slide then. So this is all about explaining what data inversion is, and here we have a blood splatter, which Maurizio tells me I think is from Dexter, a blood splatter on the wall. And so here we have a clue as to something going on, but we want to find out what event caused this. Specifically, we think this is a gunshot wound, and we want to find out where the murder took place, specifically at what height this gunshot wound took place. Okay, Chris, we can put the next slide. So this is an actual scientist working this out. You can see he's got a pole there with lots of pieces of string and ribbon connected to splatters on the wall. Chris, your mouse arrow is bouncing around the screen. I don't really want it to do that. So how did they actually do this? We'll answer if we just click the text on this. Ashanti chicken wing sauce, ivory dish soaked for blood, so that has the blood of the right consistency, artificial blood, splattered between two boards, and they just splattered it over white walls and then worked out a program which relates the blood splatter to the height of where it happened, and so they're producing software for that to happen. What happens is the police map all the heights of the blood splatter and you compare it with the height of the gunshot wound. If the points match up, you're right. If they're not matched, well, try a different height and see if that works. So this is an example of data inversion, that the results you've got are the blood splatter, and so we are trying to work out the event, the basic event which caused the splatter. Okay, perhaps at this point we should just click on me to say hello to everybody in case we haven't already said hello. Here I am, Bruce Matthews, and welcome to this particular session. Again, sorry about the delay in the start due to some not being able to get the slide online, but welcome. And the data inversion we're talking about is a fundamental property of the PoreXpert software, and this is the key to the whole thing. So if we go back to the slide, the main thing on the data inversion is to choose the correct property that you're going to invert. So we have had a look at the blood splatter. If we go back to the PowerPoint slide here, we are looking at the next slide on here, which is that we choose a property that can be inverted. And when we were working on this originally, when I was doing my original research, PhD and postdoc and so on at Oxford University, we were looking at very fundamental stuff, gas viscosities and so on. And it turned out that in terms of gas properties, the thing that you could invert was viscosity. Diffusion gave you too little information. Thermal conductivity, well, it's too much and it's all mixed up. And so when we're looking at porous materials, it turns out that analogously, the thing that we can look at is percolation. Diffusion gives you too little information, and permeability is too averaged out. People often ask us if we can invert permeability. You can't, because it's just so averaged you can never unscramble it. So if we just click on this side, in terms of percolation, we're talking about mercury porosimetry, porometry, or water retention. Okay, so on the next slide, we see that here we're just going to have a brief talk about Mercury. This is a Calder mobile. If you ever go to Barcelona, go to the top of the hill next to the Olympic Park, and there is this Calder mobile. So that's a pool of mercury, and mercury splashing around through that channel. In the old days, people just stood and admired it. Now it's all boxed in. But mercury, as shown on the next slide, is a non-wetting fluid. Here it's just some mercury bubbling out of a paper coating. It really doesn't want to be there, so it just forms these bubbles. And if we look at the next slide, it shows us how mercury goes into a material, a non-wetting fluid, interfacial tension, and pushing through a cylindrical tube. So the mercury here is shown as this pale grey-blue substance being forced into a tube. It doesn't want to go there, so it forms this bulge as it gets pushed in. But once you've got to the right pressure, you can imagine this what's called piston flow. It goes right through the tube. Okay, so on the next slide we see the equation that determines this, which is the Laplace equation. Sometimes people refer to it as the Washburn equation, but the Washburn equation is really time dependent. The Laplace equation tells you that cylinders of diameter d with a fluid with interfacial tension gamma, contact angle theta, and applied to the pressure P. Okay, on the next slide we see a typical mercury intrusion curve, and you can see that very often for porous materials we get a S-shaped curve, which is shown in yellow here, and the traditional way of analysing that is simply to take the gradient of the curve. And so in this case we would say, well, most of the voids within this material are of sizes between 10 and 100 microns, about 30 microns on this slide. But the problem with that is that it rather assumes that you can get to all these voids. If we have another look at the next slide, if we convert that gradient to number of cylinders, then in practice the number of cylinders, we have more numerically small ones because they're such small volume that you need a lot of them. The next slide shows you an actual intrusion curve. You see it wanders its way up. The blue line there is very complicated. The green line, which is the derivative, is also very complicated. This is some material we're working on at the moment for nuclear reactors, graphite in nuclear reactors. The next slide reminds us that simply taking the first derivative of the curve, that green line there, assumes this wormhole model, these bundle of capillary tubes model, and in fact it doesn't even give you the wiggliness, the tortuosity of the wormholes as shown on this particular slide. Okay, so let's just have a quick resume of what's going on in mercury intrusion. If we look at the next slide here, the mercury is shown in green. At the bottom there is the Laplace equation, so we're saying that applied pressure P1 is less than what's required by the Laplace equation, so it's less than minus 4 gamma cos theta over d1. The minus there is because cos theta itself is negative, so all of that comes out to a positive number. So you then increase the pressure as shown on the next slide, and you increase it to a point where the green mercury there is pushed into the cylinder, and you can see now that you have also got enough pressure to push it into the next void, which has diameter d2, so it fills that as well, as shown on the next slide. But you haven't got enough pressure at the moment to push it into that another smaller one, for example d3. So we have to increase the pressure to get it into d3, as shown on the next slide. Okay, so we now got it into d3, and if we plot that particular intrusion curve there, 3-pore intrusion, there we have it. We have this S curve which is appearing, nothing much to start with, then a big volume as we increase the pressure, and then the little cylinder at the end doesn't intrude very much. Okay, so we then have some complications on this, only some of which we're going to look at today. One of the complications is mercury entering a surface pore, as shown on the next slide. So sometimes you get big pores on the surface which require very little pressure to intrude. So at a low pressure, mercury intrudes. So if you add that to the other effect, as shown on the next slide here, we get an initial step. Also shown here, something we're not considering in detail today, is that if you pull the mercury out, you need to lower the pressure more than you'd expect, and so there's a hysteresis. The intrusion and the extrusion curve track differently. Also, at the top, we may find that we compress the sample, and if you do that, if we zoom in at the very top of the curve, as shown on the next slide. So here we have 10% radial expansion pushing the sample out. So the mercury, it seems you've got more mercury going in than you'd expect. And if we look at the graph that corresponds to that on the next slide, we see at the very highest pressure, there's a little step up at the top there. And if we just zoom in on that a minute on the next slide, and again zoom in on it, and zoom in again, we can see that at the very top there, not only is there this extra step, but the intrusion and extrusion follow each other. The sort of darker red line and the lighter purple-pink line. So the darker red one is going in, the dashed purple-pink line is the one coming out. And at the top, they sit on top of each other, and that is an indication that you're compressing the sample, not actually intruding. And in fact, from that, you can get a bulk modulus out of that. If we look at the next slide here, for example, some work we have done on paper coatings, we get a bulk modulus which corresponds to where we'd expect it to, which is somewhere between the mineral pigment itself, you click on the slide, and mineral plus latex binder. So we get a value about that. Okay, so the question now is, so how can we possibly go from a curve like this back to the pore structure which caused it? And so this is the big question. For this, we need some data inversion. We need to go back from what we observe to the fundamental physical process that caused it. So on the next slide, we see the principles then of the data inversion in this case. We see, if we click on this slide, this is the percolation that we've just been looking at, the green mercury going into a series of cylinders. And then from that, if we knew what all these sizes were, clicking, then we could forward and say there's a unique and calculable property shown on the right here, you click, which is the intrusion curve. But the problem now, going backwards on the slide, is that you can't go backwards, essentially. That's non-unique, you can't calculate that, so you require an inversion method. So let's just have a look at this inversion method in the case of porous materials. On the next slide, we see this laid out, and if we click on here, we see the intrusion curve. And how could we get this intrusion curve? Well, you can imagine that there are loads and loads of structures, all of which could cause that same intrusion curve. So somehow we need to cut down on the number of structures. We need to impose constraints. So we click on this slide and we see that we're imposing constraints on there. So instead of an infinite number of possible structures, we impose constraints to reduce the number of possible structures. And clicking again, we see that in practice we have an intrusion curve. We assume pore structure comprises aligned cylindrical tubes, and we see that under those circumstances, this is the wormhole model, there's just one possible structure, which is these aligned cylindrical tubes. There's the wormhole model sitting there. Okay, so if we now think, well, that's wrong, so how do we get round that? So we then have an intrusion curve. We then have a lot of infinite number of structures, so we have to assume some tight constraints. That we have a single stochastic generation, that is a single throw of the dice. We have, for example, we impose a random structure, we have some simple geometries, and we equally space the voids on Cartesian coordinates. So we put all those constraints on it, and clicking on here, we get a structure, one possible structure, which is now, clicking again, the not the wormhole structure, but another structure. So if we click again, we can see that. Okay, so it's not the wormhole structure. Clicking it again on here, it is the a different structure from that. Okay, so we're getting there. We still have a few problems though. Those are very sort of severe constraints. They only give us one structure, and it would be better to assume some wider constraints. So let's click on the next slide, and here we have again an intrusion curve. Clicking again, we assume some wider constraints, a range of stochastic realizations, a range of structure types. Clicking again, we see there is a wider range of particular structures that are possible. So how do we actually guide ourselves to these particular structures? How do we get these particular structures? So if we go to the next slide, we're looking at the principles of data inversion. And the blood splatter data inversion, the slide we looked at to start with, was in terms of just a single parameter they were looking at there, which is the height of the gunshot wound. That's all they're looking at. If we're looking at the structure of porous materials, we need a lot more parameters than that. The sizes, how they're connected, all sorts of particular parameters. So we need an automated guide to guide us towards the right answer. So here, on the next slide, we have another analogy here. This is a damsel in distress. She has been kidnapped by some villains, blindfolded, and she's thrown out an aeroplane, and she lands on a mountain range, and as she does so, she breaks one of her arms. So she's blindfolded, she can't take the blindfold off, she's got two legs, one arm, and she needs to find her way out of the mountain range. And the way she does that is feel around her with her one arm, and whichever is lower, whichever her two legs is lower, or her one arm, then she goes that way. So she's essentially contacting the mountain range in 3 points. If she was bigger and straddled the mountain range over a larger 3 points, as shown if you click the slide here, then she would sample more of the mountain range, and actually that would be better. So it's better if you straddle more. Okay, so she's going to find her way down the mountain. Clicking, we see the actual route down the mountain here. So there she follows the blue route, and she gets to this particular point here, which is a false minimum on the mountain. And then she has to decide what to do. If you look at the green arrow there, she just goes in a random direction for a certain amount of time. She then has another go of finding her way down the mountain. And again, she keeps another false minimum. She knows she's not out of the mountain range yet. So again, she goes in a random direction, a certain distance upwards, and then tries to find her way out of the mountain range again. And we follow the blue line, and now she's lucky and she gets pretty much out of the mountain range. So you can see it's a long process. If we now look at how this is represented in terms of what we're doing, we're clicking on the slide, we see that what we're looking at is a quality index. This is the distance between the simulation and the experiment. We want that as low as possible, so the height as low as possible, to get ourselves out of the mountain range. So we want to change parameters 1 and parameters 2 to get ourselves the lowest possible on this three-dimensional graph. So clicking again, we see that these, we can, looking at the distance between the simulation and experiment, And here are two of the parameters we use: the connectivity of the network and the skew of the distribution of the throat sizes. We put some more technical terms in here. Clicking on the slide, we see that we have starting points here. They form a triangle of points. More technical terms are these green arrows are known as annealing, the random direction, and where we ended up here are known as false minima. So there we have the situation. So that triangle there is known as a simplex, and it can move its way down the mountain. It can fold, expand, contract, reflect, expand, and so on. So here are some of the simplex maneuvers. And the annealing itself, which is shown on the next slide, is done in terms of a sort of pseudo temperature, because it's like annealing glass. So this is called the annealing temperature, and it follows a logarithmic function like this. Clicking on the slide, we see that every so often the annealing temperature reduces to 0.8 T, 0.64 T into 0, and so on. And clicking again, we see that the annealing temperature T is displayed in the software as the randomization factor. So this randomization factor gradually reduces. Now we put a whole lot of other stuff into the software as well. This next slide shows you that the distribution of voids we think is a continuous distribution. It could be bimodal, it could be Poisson, it could be Boltzmann, or Gaussian, it could be normal distribution, and all of those are covered by this Euler beta distribution. Clicking, we see on the bullet points here that it gives you an intuitively correct range of throat size distribution, Gaussian, Poisson, log linear, and so on. And clicking again, there is a linear variation of number of voids when plotted on a logarithmic scale. It can be bimodal. If it is bimodal, it has steep cutoffs top and bottom. Okay, so we put that in as well, and all this extra information we put in using what's called a Bayesian approach, shown on the next slide. That we are taking a Bayesian approach to this problem, which is that we put in extra parameters. We know the porosity, for example. On the next bullet point, we know from the sample size the likely range of pore sizes for sandstone soil, and we also know for some sample types the relationship between the sizes of the pores and their adjoining throats. And so we use the simplex with all of these parameters and all of this extra information. So on the next slide, we see that what we have seen is actually a two-dimensional simplex. It had two parameters, but we use an 8-dimensional simplex within the software. It's called a Neld amoeboid simplex. The annealing is a Boltzmann annealing. On the next bullet point, we see that there are 5 parameters, which is the throat size distribution, spread and skew of the pore size distribution, the connectivity of the network, and the short range size autocorrelation function. And clicking again, we see there are also 3 Boolean parameters: porosity, achievable, structure drawable, network fully connected. Okay, so that's all the theory of it. Any questions at the moment from our participants? Michael, do you have any questions at all? I realise you're not going to talk to us about them because you've got a bad throat, but if you have any questions at this moment, what we're going to do now is just go on to a demonstration of the software and actually see it in action, and then as usual all it becomes clearer. Okay, well, I can't see any questions from Michael, so let's swap to the software itself, which Chris is going to switch on for us. Are you going to screen share for us, Chris? So what we're going to do now is look at the software converging on a simple sample, a nice simple S-shaped curve, not one of those curves that wanders up. So as soon as Chris has got the software loaded up, we shall have a look at it. How are you doing, Chris? Right. There we go. So this is the PoreXpert screen, opening an existing file here. So we just find for demonstration purposes, a nice simple sample. This is one of the example files loaded into the PoreXpert directory, which will be loaded onto your computer when you load the software. So here we just have a Clasher outcrop sandstone, simple S-shaped curve, and we have dimensions here. Just for demonstration purposes, perhaps we should just reduce the size of the cell there. So we're going to just do a very, very small cell. While we're at it, we can look at the advanced menu there. And the advanced menu, if you look there, you notice there's a learning mode. The software learns as it goes on. And here we have things that control how the simplex moves around parameter space. You don't really need to change these unless you particularly want to. We in general never change them. And then further down on the advanced menu here we have simplex limits. So these are these various parameters which cover this range. And if you want to sort of restrict the simplex to converging into a particular sample, then you can alter these parameters. Normally the only one we change is this thing called pore skew suppression, which stops this bulking up parameter. It sort of suppresses the bulking up parameter if you wanted it to be suppressed. Okay, so those are all the parameters. I don't know whether you want to put the pore skew suppression down for this one, Chris, or whether you want to leave it up there. So that's a one that can be altered if you want to. You go accept, and then what it's doing now when it says setting up the starting grid, that's the equivalent of the woman on the mountain range spreading her arms or her one arm, because she's broken the other arm, and her legs, spreading her legs as far apart as she can, and her arm as far apart as she can. Remembering that the further apart that you can spread it, the better you can sample the mountain range to start with. So when it sets up the starting grid, it doesn't try to find the best answers to start with. It tries to find a range, some good, some bad. So it straddles parameter space. And when that number there gets to 50%, it will have done that, and then it will start moving the simplex around, which we'll see in a second. And we also see the graph on the curve. So that's its attempt. You'll see the white line, which is the simulation, converge onto the red dots. You also see there's the randomization factor. That's this annealing temperature we're talking about, which is gradually dropping, now down to 0.6, 0.3, and so on. And you can see as it does it, the simulated curve converges onto the experimental points. It doesn't make any assumptions about what's in between those red dots. All it does is converge onto the red dots, and you can see it's done quite a good job of that. Okay, so we accept that, and then in fact there's the structure shown in the little panel there. You can see it's quite a small structure. We can generate much bigger ones than that. So there you have seen the simplex in action, and luckily all the things we've been talking about, the Bayesian statistics and the maths and so on, the Euler distribution, it's all in there, it's all automated, so you don't need to worry about it, but it's nice to know that it's all there working for you. Okay, so if we go back to the PowerPoint slide now, we can see a much bigger structure that we have done previously. The bigger the structure, the less repetition you get. So therefore the more realistic it is, because all of these structures connect together like Lego bricks, and if it's a small structure you get a lot of repetition. So here's one of these bigger structures, and we're going to simulate the Mercury intrusion going into this. So clicking on here, the mercury intrusion is going to be shown grey, and it's going to go in from the top surface. On the left there you can see the applied mercury pressure, currently 0 with no 0 uptake. Clicking on the slide we can see mercury going into it from the top. So there it goes, initially on the top surface. Clicking again we can see it gradually fill the structure. So we're now going to watch the pressure gradually go up, and as we do you can see mercury penetrates the structure. You can see it's very heterogeneous. It doesn't fill up in any way in a sort of linear front. It goes into the biggest first, and it can go round and dodge bits and so on. It goes in a very heterogeneous manner. And there you can see it's almost full. There's a couple of little voids which are still empty. Okay, so if we go on to the next slide, what have we achieved by this data inversion? A structure. We have achieved a structure which, clicking on here, is fully connected in 3 dimensions within itself, and it also goes to adjacent replicates. We have achieved a structure which matches the porosity and the entire percolation characteristic, for example the mercury intrusion curve of the experimental sample. Clicking again, we have achieved a structure which has got other geometric relationships built into it. For example, local size autocorrelation, the relationship between sizes of pores and adjacent throats. So it's got all of this additional information built into it. It has got simplifications in terms of void shape, cubes and cylinders, but for many properties these don't matter. It's just in terms of volumes and cross-sectional areas, and it's a much more realistic structure than the wormhole model, so it's realistic enough to be used for a large range of other properties. For example, on here we've listed absolute permeability, filtration characteristic, microtoning, many others. It's not unique, so in practice if you wanted to use it for research purposes you need to throw the dice again, do different stochastic generations and generate lots of structures, and so well, of those lots of structures this particular one has got all parameters which are close to the mean of the parameter bunch, so that's called getting a representative structure. So we have to remember that it's not a unique structure. There are lots of ones that will do, but you can do some studies on that. And clicking again, so just a reminder that we use a representative structure, and again a reminder that once we've got the structure, the important thing about it is that we can then change its geometry, and by doing so we can try and predict the effects such as weathering, combustion, changes in production parameters. Okay, well I hope that's given you a sort of insight into data inversion. Any questions from anyone? Okay, well, so that's a training then on the data inversion. I hope that's been clear and enjoyable. Remember that the data splat, or the blood splat on the wall, and that's all to do with data inversion, as is the PoreXpert software. So thank you for participating, and we'll see you again soon.